In this video, we're going to introduce you to logarithmic functions, and we are going to be comparing it to the basic exponential function, which is y is equal to b to the x. So what we're doing first is we're starting with a simple exponential function. Remember, exponential function means the variable is in the exponent, and we're going to be putting values down here. So for example, when x is 0, that means 10 to the 0 is going to be 1. Anything to the 0 is 1. Then we have 10 to the first is 10. 10 to the second is 100. 10 to the third is 1,000, and so forth. And when we're looking for the the inverse of the exponential, remember the inverse just simply means that we swap the x and y. So in the same way, we're going to swap the x row and the y row. So y to the 0 is 1, y to the 10 to the first in y is going to be 10. And what I'm doing basically in any inverse, we're switching the x and the y. So I can simply, without even doing math, I can just simply reverse the x and the y rows here. And to show you what this graph looks like, I wanted to show you the graph of both of these functions here. Where when we look at both of these graphs, the blue here is going to be that exponential function. Again, it's crossing at 0, 1, or 10 to the 0 is 1, and then it shoots up extremely, extremely high. This one is the reverse, where my x and y are reverse. And if you remember from any inverse is a reflection over this green line, over this y is equal to x line. And if you think about it, if I folded this graph in half, the red and the blue would match right on top of each other. Again, if I fold it along this y is equal to x line. But what we have to do is we have to find a way in order to solve for the y. And what we have is we have the logarithmic function. So logs are basically the inverse of our exponential functions. So what they did is they found basically a way to solve, again, to solve for this y value. Remember, every time to find the inverse, we switch the x and the y, and then we solve for y. But there's no real way to do that until we had logs. So what we're doing is basically we're rewriting our exponential in a different way. So if you notice, I wanted to point out a couple of things. First of all, we have the base is b, and the way we read this is log base b. And remember, the whole point is to solve for the exponent. So the answer to your logarithmic function is the exponent on the original. And then the y is going to be the answer on the side. I don't really always have a very good way of remembering the y part or the answer to the exponential, but if I remember that the base is the base from the exponential, the answer to your log is the exponent, then the y falls in line the other direction. So here's a little reminder. Again, b is the base of the exponential, x is the exponent of the exponential, and then the y falls into place. So if I wanted to put these into log form, this is just simply memorizing a rearranging. So we have the base. So this means I'm going to say log base 2. This is the base. So I would have said log base 3. This is the base. The base is the thing that's being multiplied over and over and over again. So this is going to be log base 4. Then the answer to my log is going to be that exponent. The answer to that log is going to be the exponent. The answer to that log is going to be the exponent. And then I don't have a great reminder, but it's the last thing that's there. And we can go in reverse. The base of the log is the base of the exponential. The answer to the log is the exponent. And then the other thing is the other value is the answer to your exponential. So this is, pause if you want to, but I'll talk in a second. This is log base 2, so I have 2 to the exponent 4 is equal to y. Log base 5, the answer to the log is the exponent is 125. So in this first thing, just putting into one direction or the other is simply just getting used to where things got rearranged, whether we're having in my exponential function or my logarithmic function. Just getting used to putting one into the other and being able to switch between the log and the exponential is going to be extremely helpful when solving some of these. So let's look at a couple of examples. So if I'm looking at these first example of exponentials, these are relatively easy to solve because I know that 3 squared is going to be 9, so x is simply 2. In this one, I know that 3 to the third is 27, so x is 3. So in these first examples, it's really easy to solve. But in this one, it's not so much. We can't get an exact answer for this because it's going to be somewhere in between 3 and 4. But what we can do is we can convert this into log notation, and we can start to solve and possibly find a way to figure out x3 to the something somewhere between 3 and 4 would give us that answer of 50. So pause the video and I want you to convert each of these exponential functions into log form. For example, log base 3 of 9 is equal to my exponent. So pause the video and do that. And hopefully that was relatively easy because in each one we are simply looking for the exponent of the same base. So I have the same x, the same base, and just looking for different values of the answer to my exponential. So 9, 27, 81, and 50. And then this is the nice, pretty, formal way of writing this up. So here's a little bit more practice about putting things into either from exponential into logarithmic or logarithmic into exponential. So please pause the video and do that. So here's all the answers to these ones. And if you notice, I skipped over this ln of x, and we haven't talked about this. What we have is we have two specialized logarithms in which the base is inferred. So if you remember, like if I write x, we understand that that means that that's the same as there's a 1 understood here and a 1 understood here. There's some certain things that are taken for granted in mathematics. So when we see something like ln of x, what that means is that means log base e of x. Now we may not be familiar with e because e is a new constant we might not have seen. So if you look on your calculator, you actually have an e button, and if you type in e to the first, you'll end up with something like 2.7818, so on and so forth. And this constant is actually 7. I messed that up. There we go. That constant is something that is used in different exponential functions. That's used in the natural log. And it's something basically like pi. It's just a constant number that we accept. Anytime you see the letter e, it is representing this 2.71828 and so on and so forth. So what this is actually saying is log base e of x is equal to y. And again, to write that in exponential form, you do your base, your answer is your exponent, and then the other part is your answer. As of note, the other understood or common log is what is known as log base 10. That is the button you see on your calculator. If you ever see, like if you're asking log base 10 of 100, you can say log of 100, and that means the exact same thing. So let's put that real quick into exponential form. So if I say log 10, that's understood to be log base 10. So that's saying 10 to what number is 100? Well, we know that 10 to the second is 100. So punch that out on your calculator. If you hit log of 100, it will be equal to that exponent, or that 2. And that's a good thing to keep in mind because we can't just hit log of anything else. For example, on this one, I can't hit log of 1. Oh, actually, I could, because log of any base of 1 is equal to 0. But let's say this one, log of 5, you can't hit 25 and you'll get 2 or anything like that. So we have to be careful that when we hit log on our calculator means log base 10. That's a very specialized log. And then again, ln or natural log means log base e. So let's look at some of these logs, and putting them into exponential form will actually help us out. So if I look I'm going to set these all equal to a variable just to help me out, so I can sit and think about where this is going. Now, some of you might be able to visualize. It's just looking for my exponent. So let me turn it to black. So you might be saying, oh, asking 10 to the what is equal to 10. But for those of you who can't visualize it, let's put it into exponential form. We have the base, the exponent is equal to my answer. So 10 to the first is equal to 10. Putting this into exponential form. 10 to the x is equal to 100. Well, we just talked about that x is going to be equal to 2, or that's equal to 2. This is saying 3 to what exponent? Or again, putting into exponential form. 3 to the x is equal to 9. So that's 3 squared is equal to 9. This is asking, 9 to the what is equal to 1? Well, anything to the 0 is equal to 1. Incidentally, log to any base of 1 is equal to 0. So this can be any base at all. That's a nice fact to have in your pocket. I have here 5 to the x is equal to 125. Well, 5 times 5 times 5 times 5, or 5 times, yeah, 3 times is equal to 125. Now I want to look at this. There's no base written. Remember, if there's no base written, it's understood to be log base 10 every time. So this is x to the 10th is equal to 0.0001. That is 1/10,000th. So x, or 10 to the x, is equal to 1 over 10,000. Now here's where we get into something here. When we're going to a smaller number, we're actually raising to a negative exponent. So this value here is going to be negative. So what we're doing is we're flipping this over, or 10,000 is x to the 4th, but 1 over 10,000 is 10 to the negative 4th. So this x is equal to a negative 4. So looking at these specialized logs, again, when it's not written, this is understood to be log base 10. So if we tap it out on the calculator, we can find these really easily. So for each one of these, I simply tapped it out on the calculator. And let's talk about what this means. Remember, these are each log base 10. So what this means is 10 to the 0.845 is equal to 7. This means 10 to the negative 0.602 is equal to 0.25. And what I want you to do is actually tap that out, see if that makes sense. Type in 10 to the negative 0.602 and see if that equals 0.25. ln is the natural log. That is log base e. So what this is saying is that e to the 2.565 is equal to 13. This is saying that e to the 2.71 is equal to 15.029. I can put that back into log form. Log base e of 15.029 is equal to 2.71. Or again, you can type in natural log of 15.029 is equal to 2.71. So what we can do is we can actually use that idea to solve. And when I'm glancing at logs right now, I'm not super familiar with it, but if I put it into exponential form, and that's one of the first things, first tips to solving exponential or logs. Sometimes switching between log to exponential or back to log, either way, can help us to visualize the answer. So if I can't see it this way, I have no idea what this means, I can go log base 10, so I can go 10 to the x is equal to 1,000. Well, hopefully we know that, again, the number of zeros kind of indicates the power of 10, so that means x is equal to 3. And again, because this is log base 10, I can punch that on the calculator. So in this one, I'm saying log base x, I don't know, but this means x to the 4th is equal to 16. Well, that's 2 times 2 times 2 times 2, so x is equal to 2. So this is saying 2 to the 0 is equal to some number, well, anything to the 0 power is equal to 1. This is saying 4 to the 2 is equal to some number. Well, obviously 4 squared is 16. So even if we're not really familiar with the logarithmic functions, we can definitely put it into exponential, and sometimes the answer becomes a little bit more clear. The last part is to consider what happens when, if I put it into exponential form, it doesn't do us any better. So I'm going to go actually down here, putting this into exponential form. I've got 7 to some number is equal to 100. And looking at the powers of 7, again, 7 to the 2 is 49. 7 to the 3 is 343. So I know it's somewhere between 2 and 3, but I can't. That's not a nice, pretty, perfect power of 7, so that's not going to help me out. So in order to do this, I need what's called the change of base formula. So what we're going to do, instead of putting into exponential, which doesn't help us a lot, we're going to use this change of base formula. And what we're going to do is this. We're going to, first of all, I'll give you the general form, which is log base A of B. So these two mysterious A's and B's is saying I can take the log base C of the top and the log base C of the base. So if you notice, again, it's the same base here, or number here, and then the same base here and here. So essentially what we're saying is that I can use another log to help me figure this out. So let's look at that example we had earlier in the video, where I have putting this into log form, it's log base 3 of 50 is equal to x, and we knew it was somewhere between, again, 3 squared is 9, 3 to the third is 27, and 3 to the fourth is 81. So I know it's going to be somewhere between 3 and 4. But using this idea is what we can do is we can use a definitely different base. Well, why don't we use the ones that are on our calculator? So I'm going to use a log base 10, which is we don't write anymore, of the big number over log base 10 of 3. So do yourself a favor real quick, pause the video and type that out. So when dividing the log base 10 of 50 by the log base 10 of 3, I get this 3.566, which again is between the 3 and the 4 that I thought it would be. It also makes sense. If I wanted to check this out, I can raise 3 to the 3.5616, and I will get approximately 50. Now we are rounding our values, so we're going to end up with something slightly off, but we are getting the approximate answer. And remember, when we do this, it's the log of the same exact C, or same base each time. So we have C here and C here. So I could have done the exact same thing if I chose log base E. So what if I did the natural log of 50 over the natural log of 3? Same base, that's what's important, is that I have the same new base here. But again, it's one that I can type out on the calculator. So I'm going to punch these out. Using the natural log as my double base, or using the log base 10 will still give me the same 3.566. So when I'm looking back at this log base 7 to the 100 right here, so let's go and figure out doing the same thing. We have the log of 100 over the log of that original base. So it's the log of this number here over the log of the base. So we're going to divide that out, and it should be somewhere between 2 and 3. And I get 2.367. So the next thing you're going to do is you just make sure, this is just testing it out, is saying if I actually do this, if I put this value in, I'm going to erase this value here, but if I say that 7 to the 2.367 will I get at 100? And that's a great way to check yourself, because right now it feels kind of arbitrary, like I'm just punching numbers in, but the whole goal is finding the appropriate exponent here. So if we've done the change of base formula appropriately, then we should get that exponent that works into our original equation. So pause the video and evaluate each one of these. Hopefully these were some of the answers that you got. If you'll notice, the answer is actually looking for what exponent it is, and what I had in each time is the check to make sure that, yes, in fact, my base to this new exponent is in fact the answer that I'm looking for. That my base 7 to this new exponent that is the answer was the original that I was looking for. I did want to point out here on this problem here that I asked for log base 500. Well, that's exactly what log base 10 is. So that was kind of a sneaky problem. Like, I'm asking the same thing, because some of you, when you hit log base 10, it's like, oh, it's 1. This divided by 1 is the exact answer. Because in asking for log base 10 and doing log base 10, this is exactly the same question. So this really didn't need the change of base formula. So hopefully some of you noticed it. If you have any questions, you can definitely contact me.